Assalamu alaikum. Hello everybody. This is an exercise about sequences. The first sequence is this one. Prove using the characterization and epsilon. Prove using the characterization epsilon and epsilon that the limit of n a power n when n goes to plus infinity converge to 0 such that the absolute value of a is less than 1, strictly less than 1. Actually, we have two methods for this, the first sequence. First method, we need to prove that, we need to show that for all epsilon greater than 0, we can find a rank n of epsilon which belongs to n, such that for all n greater than or equal to n of epsilon, this implies that the difference between un and 0 is less than or equal to epsilon. The negation of this property is, we take the negation is there exists epsilon greater than 0 such that for all ranks from n there exists n greater than or equal to n of epsilon, and the absolute value of n is greater than epsilon. So one has, we suppose that there exists epsilon such that for all the ranks we can find an index which is greater than n epsilon such that this is true. So what we have? We have that n a power n which is equal to n absolute value of a power n is greater than epsilon. This implies that since the logarithm is a non-decreasing function, so the logarithm ln of n absolute value of a power n is greater than ln of epsilon, and this implies that ln n plus n ln absolute value of a is greater than ln epsilon. If we divide both inequality by n, we get ln n over n plus ln absolute value of a, which is greater than ln epsilon over n. And we remark that for all ranks we are able to find n, so we can take n of epsilon as large as we wish, since for all n of epsilon. So this tends to 0 when n is sufficiently large. This goes to 0, and this also goes to 0. Thus ln is greater or equal to 0. And this simply shows that the absolute value of A is greater or equal to 1, which is in contradiction with this hypothesis. This means that we can rank exist, so a rank can exist. This is the first method. The second method let us consider function f of x, which is equal to x squared, absolute value of x, absolute value of a, power x. Sure, a is different of 0. If it is equal to 0, f of x is equal to 0. The same thing with the first case. And which is equal to x squared exponential x ln absolute value of a. Let us calculate the derivative. The derivative f prime of x, x is greater than or equal to 1. We take our function from x strictly greater or equal to 1. Calculate the derivative. F prime of x is equal to 2x exponential x ln absolute value of x plus we have the derivative of the power, so ln a x squared ln a power x ln a, which is equal to x exponential x ln absolute value of x times 2 plus x ln absolute value of a. ln absolute value of a, this is a negative number, so the derivative is negative from what point? From the point x is different of 0 is greater than 0, 1, so positive. This is positive, so the sign of the derivative depends on the sign of this polynomial. 2 plus x ln absolute value of is less than 0. This implies that x is greater than minus 2 ln absolute value of a, and we switch the sense of the inequality because ln absolute value of a is negative. So f of minus 2 over ln absolute value of a, this is equal to what? This is equal to, we're replacing the function, x squared means 4 over ln a squared times exponential x ln a minus 2 ln, we cancel ln I with ln I, so we keep exponential minus 2. Then the highest, the greatest value is at this point for a fixed one, sure. Then what we can do later, we can consider, so consider and great, we start from and greater than what, or equal to the integer part of 4 over ln I exponential 2 square plus 1. I reformulate just this one, exponential, okay. I will explain in a few minutes what I am writing this way. So, for all x greater or equal to 2 over e ln absolute value of the square, we can deduce that f of x is less than or equal for all x greater than or equal to minus 2 ln I, we can deduce that f of x is less than or equal to this value, 2 over I ln I square. This is a peak for all the incoming value. Then for all n greater than or equal this value, we can imply that n square a power n is less than or equal to what? Sorry, once again. Minus 2 and ln absolute value of for all n which is greater or equal to this integer number, n square absolute value of a power n is less than or equal here minus 2 over ln a plus 1. N square absolute value of a power n is less than or equal to the previous value, this one which is 2 over a ln absolute value of a square. This means what? This means that n absolute value of a power n is less than or equal to 2 over a ln absolute value of a times 1 over n. So it is sufficient to take this less than epsilon. From what we can deduce, that n is great or than n is greater than this value over epsilon. Yeah. So it is sufficient to take n of epsilon equal to the integer part of 2 over a ln a square over epsilon plus 1, and someone is happy. Yeah, I am very happy for this solution. The next exercise, the next sequence is Vn. Vn Vn equal to the square, the nth root of n, and we need to prove that this goes to 1 when n goes to plus infinity. There is a little trick here to deal with. If n is equal to 1, the 1th root of 1 is equal to 1. If n is equal to 2, the square root of 2 is equal to 1 point and so on. So let n be greater or equal to 2. Then the nth root of n is equal to 1 plus Rn. Rn is a positive number, strictly positive number. Rn is a strictly positive number because the nth root of n is greater or equal to 1. What we can do later, we can do that. We can deduce that the power, we take this to power n and this one, so we will get power n, this is equal to n, which is equal to 1 plus r, it depends on n, Rn, power n, this is power n, which is equal to, this is equal to the sum from k equal to 0 to n, Cnk, or we can write it in English way, nk, 1 and r n minus k, or we can take k. It is symmetric, which is greater than or equal to 1 plus n times n minus 1 over 2 r n square. Yeah. And from this side we have n. We have n. And this Rn square, actually, this Rn square, Rn is equal actually to the square, the nth root of n minus 1. So if we take square here, here we take square. Then we get n greater than or equal to 1 plus n power times n minus 1 over 2. The nth root of n minus 1 square. Yeah. This is the magic formula. This is the magic formula. From what we can deduce that, we take this from this side, we get n minus 1 greater than n times n minus 1 over 2 times the nth root of n minus 1 square. So this will goes with this. 2 is 2 over n is greater than the nth root of n minus 1 square, which implies that the absolute value of minus 1 is less than the square root of 2 over n. And arrive at this level, we can just consider that this is less than or equal to epsilon. Then we get n greater than or equal to 2 over epsilon squared. So we can take n of epsilon equal to the integer part plus 1. And once again, someone is happy. Thank you very much. See you next time.